Okay, let me share my screen. So, are you all able to see my screen?
Yes, ma'am, it's visible.
Okay. Okay. So, okay. So I once again welcome you all for the week 6 live interactive session for the course polymers concepts, properties, uses and sustainability. Okay. Now let's go to the brief recap of lectures of week 6. So again, week 6 was based on physiochemical properties, mechanical and electrical properties of polymers. So lecture 38 was on physical and chemical aging, right? So it was based on sustainability. So aging process in polymers were discussed, right? So aging due to different effects, like for example pH, UV radiation, oxidation, right? All were discussed, right? Are you all there?
Yes, ma'am. Yes,
Yeah.
ma'am.
Yes, ma'am.
Yeah. And then chemical and physical aging, where in case of chemical aging there is a chain scission and all, right? uh, were all discussed. Whereas in case of physical aging there is a reorientation alone. Reorientation here, in case of chemical aging you have chain scission and all, right? And then examples of aging like degradation of polyisoprene due to photooxidation or ozonation. And then aging in case of wood, like aerobic and anaerobic root. And then destruction through microorganism were all discussed, and how the functional group changes due to the aging process. Uh, and how do you identify the functional group using FTIR were all discussed, right? And then property changes, orders of magnitude of change in properties due to aging was also discussed, right? And then accelerated testing, where you can actually identify the lifetime of the material was also discussed, where some stringent conditions are put forth, like some accelerated temperature, like higher temperature, or all put forth. The material subjected to different testing, and the age can be identified, the right. And this was followed by lecture 39, so solution properties. So this is based again on properties of the polymers, especially on the in solution. So the concept of overlap concentration was discussed, and then intrinsic viscosity was introduced, theta temperature, and then solubility parameter, right, were introduced. And molecular solvent interaction, how does it help in determining the molecular size. And then orientation correlation and persistent length, and then persistent chain was also discussed, right? Did you all go through?
Yes, ma'am.
Yeah, are you able to recollect?
Yes, ma'am.
And then lecture 40 was on conducting polymers, where electrical conductivity was discussed, right? The mobility of charge uh, was discussed. And then conducting polymers, how in case of electronic conduction, conjugation, it helps in electronic conduction, right? And in case of polymers, so there can be groups that helps in electronic conduction, right? And then all polymer device was discussed, and the different applications like inflexible electronics, sensors, actuators were all discussed, right? This was followed by lecture 41, where dielectric response uh, was discussed. So So two types of responses: linear response, where a material is subject to a lower perturbation and there's no major structural changes or significant structural changes in the material. Uh, Whereas in case of non-linear response, there's a significant structural change, right? Like non-linear response includes like some yield or fracture mechanics, and then your electrical breakdown, all these comes under the non-linear behavior. And then complexity in response of polymers due to different levels of relaxation, and the material having both energy storage and energy loss were all discussed, right, in lecture 41. And then in lecture 42, the dielectric responses, again on dielectric response and response of materials to electromagnetic radiation, right, was discussed, where again dielectric spectroscopy was discussed in uh, and then dipoles formation in polymers, that is polarization, where orientation polarization was discussed, and then molecular relaxation, and then d by relation was discussed, right?
Yes, ma'am.
Yeah. And then Kolkol plot, Nyquist plot, right? So what is the x-axis and y-axis in case of a Nyquist plot or a Kolkol plot? Say for example in case of dielectric response. Someone remembers? And what would be the shape of the plot?
I'm semicircular in shape. Like,
Yes. Yes. So what versus what is plotted? So
it's epsilon double prime and epsilon single prime.
yeah, so epsilon double prime in the y-axis, that is the dielectric loss in the y-axis, and the dielectric permittivity in the x-axis is plotted, and you will get semicircles. And in case of real polymers, you will get multiple semicircles due to multiple relaxation levels, right?
Yes, ma'am. It's not actually semicircular, ma'am. It tends to be a semicircle.
Yeah, yeah. And then lecture 43 was on plasticity, where yield strain, and then strain softening, hardening were all discussed. And then models for plasticity was discussed, like Eyring model, and then Ramberg Osgood model was all were all discussed, right? And the final lecture was on properties of composites, where size, shape, and type of fillers plays important role, and how premixed form it helps in easier processing are all discussed. And then composite properties as a function of the constant properties, like parallel and series mixing rule, Halpin psi model were all discussed. And for composites, not only the amount but the distribution and orientation of fillers or reinforcements also plays a critical role in deciding the property, right? Like your percolation threshold, or in some cases you concentrate the fillers in particular area to add strength to that weaker area, right? The volume fraction of fillers, and then processing, thermal and electrical conductivity of composites were all discussed. And then dilute systems, where Maxwell model was discussed. Maxwell model, again here, this is for this electrical and thermal conductivity. You will come across this Maxwell model when you go through viscoelasticity also, but that is completely different Maxwell model. Okay, now let's get on to the practice assignment session. Okay, question number 1: a sample of natural rubber cis 1,4 polyisoprene is vulcanized such that one of every 240 chain carbon atoms are cross-linked. The formula unit of isoprene monomer is C5H8. and the molecular weight of this isoprene monomer is 68 gram per mole. So what is the average molecular weight between the cross-link? This is a very recent GATE question, GATE 2021 question. So what is all given? Hello, are you all there?
Yes, ma'am.
So what is given in the question? What are the information given in the question? You can just go through the question and say, right? So the information given are, first, natural rubber is there, which is vulcanized. Okay, it is vulcanized in such a way that there are 240 carbon atoms between each cross-link. Okay, and they have also given the formula for the isoprene monomer and its molecular weight, and they have asked the average molecular weight between the cross-link. So how do you estimate it? Any thoughts? There is nothing right and wrong. Whatever you think, you can just say. Are you able to understand the question? What they have asked? Sorry. Okay. So, no thoughts, is it? Okay. So shall I solve the problem?
Yes, ma'am.
See. So as I said, its natural rubbers is 1,4 polyisoprene, and the molecular weight of isoprene monomer is given. And then number of carbon atoms between cross-link is 240. Right? That is also given. Now, what is the biggest thing is that this 240 carbon atoms, it will it is a part of how many isoprene units? That is the biggest question. So if you polymerize isoprene, this is the structure of isoprene unit. So you will get into this kind of a structure which I am pointing to. You will have CH2 C, CH3 double bond C, CH2H. Okay, where do you all note one thing? What is happening here? So someone can tell me how many carbon atoms will in a particular unit will be there in the backbone from isoprene? Just look into the figure and you can say how many carbon atoms will form the backbone and how many will be in side chain for a particular isoprene
Ma'am, it
unit.
said 4 in backbone and 1 in side chain, that's CH3 group.
Yes. Yes, you are right. So others, are you all able to identify? The backbone is CH2C double bond C CH2. This is the backbone. Okay, this CH3 and H. I mean, of course, here H is fine. Here CH3 is in the side chain. So this is in the side chain. I mean, sorry, side group it is. You are all able to understand and identify that?
Yes, ma'am.
Yes, ma'am.
Okay, fine. So now the between cross-link 240 carbon chains are there. So now how will you calculate the number of isoprene units? Okay, so the number of carbon atom on backbone per isoprene in unit is 4. So what you have to do, so there are 240 carbon atoms and each isoprene unit will contain 4 carbon atoms. So the number of isoprene units will be 240 by 4, right? Are you all able to understand?
Yes, ma'am.
Yeah. So 240 by 4, that is 60. So 60 isoprene units. So the average molecular weight between the crosslinks will be number of isoprene units between the crosslink into molecular weight of isoprene units. Right? Right?
Yes, ma'am.
Yeah. So that will give you 60 into 68, 4080 gram per mole. Okay. Now next. Flexible PVC tubes are used for watering. If some organic solvents are passed through this tube, it becomes stiff. Why is it happening? This is due to the fact that the organic solvents plasticize the PVC and raise the TG, or remove the plasticizer and raise the TG, or remove the plasticizer and lower the TG, or react with PVC and increase the TG. What is the answer? What is your thoughts?
Ma'am, is it option C? Because TG, if it's lower than it is glassy state and it's mentioned it's stiff.
I think it is A. Plasticize the PVC and raise because it make plasticizing will make flexible.
The question
Ma'am,
says
it should
become
be
stiff.
C.
It becomes stiff. From flexible, it becomes stiff.
Okay, for
Option
making it
B,
stiff,
ma'am.
yes, option C is better.
Okay. Now let's see the answer. It's actually remove the plasticizer and it traces the TG. Okay. So what happens is that the organic solvents, that's what the plasticizers, it gets dissolved or diffused into the organic solvents, and then the TG is raised. Okay. The normal TG for in case of I think PVC is around I guess in the range of hundreds, but due to plasticizer it becomes lower than room temperature. But what happens when organic solvent is added, this plasticizer gets dissolved out or diffused out, and again the TG is raised. So when the TG is raised, it again, so it is in its glassy state, right? And then it is stiff, right? You're all able to make sense? Hello?
Ma'am.
Ma'am, can you say it with numbers, ma'am?
See, say for example, the uh, normal glass transition temperature of PVC is in hundreds. Okay, so what that is pure PVC. Okay, without plasticizer. But when these plasticizers are added, what happens? Your TG is reduced and it becomes plasticized. Okay, so it becomes more flexible, right? And it is, the plasticizer ratios may be added in different levels, or different type of plasticizers may be added, so that they push the glass transition temperature to below room temperature, so that at room temperature it is in its rubbery state and it is flexible. But and this can be used for watering. But instead of water, if you pass some organic solvents, these plasticizer molecules may diffuse out into the organic solvents. Along with the organic solvents, it gets diffused out or it gets dissolved by the organic solvents. So there's a loss of plasticizer. So once the plasticizer is lost, again your Tg is raised, right? So again, say for example, if the Tg because of plasticizer, if it is 18 degrees, now due to the removal of plasticizer, there will be some loss of plasticizer. Maybe entire plasticizer might not be removed. Okay, so what happens is that once your plasticizer is removed to some extent, your Tg may raise to, say for example, 45 degrees. Okay, when the Tg is raised to 45 degrees, then above 45 degrees only it will be flexible, right? It will be in its rubbery state, right? Below 45 degrees it will be in glassy state and it will be stiff, right?
Yes, ma'am.
Yeah, that is what is happening here. Okay, are you all able to make sense now?
Yes, ma'am.
Yes. Everybody is fine? You're able to understand, right?
Ma'am.
Yes, ma'am.
Okay, fine. Now let's go to the next question. The correct statement with respect to electrical property of polymeric materials is: for non-polar materials, dielectric constant is independent of frequency and temperature. For polar materials, dielectric constants depend on frequency but not on temperature. For non-polar materials, power losses are high and depends on temperature and frequency. For polar materials, power losses are low and independent of frequency. This is again a gate question. The previous question was also gate question. This question is also gate question. So tell me which sentence is correct. Are you all there? So tell me which sentence is correct.
Ma'am, is it option A?
So do all of you agree, or do you have some other option? And whoever answered it, you have to say why do you choose that option.
Ma'am, for non-polar materials, the net dipole moment should be zero, so it should be independent of frequency and temperature. Then zero is a constant, so dielectric constant.
Okay. Okay. Do you all agree with that? Do you all agree with that? Anybody else? You have any other answer, or do you agree with that? Someone who answered it? Vasu answered it, is it?
Yes, ma'am.
Okay. Anybody else? Shweta, what is your thought? Uday Kumar, Mohammed.
Yes, ma'am. I agree with you.
Okay. Okay. What you said is right. So non-polar materials, your dielectric constant is independent of frequency and temperature, because you will have some residual or very minimal dielectric constant, and it really doesn't depend on frequency and temperature because the material cannot be polarized, as you said. Okay. Okay, let's go to question number 4. This is again a gate question. In a unidirectional carbon fiber vinyl ester composite, the ratio of moduli of the carbon fiber to that of vinyl ester is 35. and the fiber takes up to 50% of cross section. The percentage of force taken up by the fiber is, what is the percentage of force taken up by the fiber? This is again a gate question. I can just give you one clue now. We solved a very similar line question, but in a different format last week. That is one clue. So what are the information given? Hello?
The ratio of modulus is given.
Okay. Okay, so which is having higher moduli?
Carbon fiber.
Okay. And then what else is given?
Vinyl ester as polymer.
Okay. I need now someone else to answer. What else is given? So what does it mean by saying that the fiber takes up 50% of the cross section? What is this information about? What does this sentence say? Anyone else?
Concentration.
Yes, concentration. Okay. How can you take it into the calculation part of it? In what way you can take this 50%?
And can we take vinyl ester as matrix and carbon fiber as filler something?
That is the fact. I'm asking this 50%. How do you take it? It's actually your volume percent. So you can take it as volume fraction as 0.5, right? Volume fraction of fiber is 0.5. Similarly, volume fraction of the polymer is also 0.5, right?
Yes, ma'am.
Okay. Now, how to proceed? How do you proceed? Someone is trying.
Using parallel addition mixing rule, ma'am.
Is it parallel addition or series addition? You're somewhere close now.
Unidirectional.
Yes. Unidirectional. That is one clue.
E1 plus E2 equal to capital E, ma'am.
Huh?
Is it E1 plus E2 equal to capital E?
Is it E1 plus E2 equal to capital E or something else? You have one more information here given, right? Just now we discussed on one thing.
Volume fraction.
Yes. So will E1 and be equal to, sorry, E will be equal to E1 plus E2, or is it sigma will be equal to sigma 1 plus sigma 2, or epsilon will be equal to epsilon 1 plus epsilon 2?
Ma'am, is it parallel addition or a serial addition?
That you have to say. That is what I'm asking. If I say that, that is what is the answer, right?
Yes, ma'am.
Again, that you can identify from the question itself. There is a sentence in question which will help you identify whether it is a parallel addition or series addition. Which sentence of the question? I've given you one more clue.
Unidirectional carbon fiber.
No. That might.
That 50% cross sectional area.
No.
Ratio of moduli.
No.
And we have covered almost all things in the question.
You've covered
Post taking
almost.
up one.
Huh?
Post taking as a whole, it's as a whole, so it should be CD parallel one.
If you just read through the question again, the last part of the question is they've asked the percentage of force taken up by the fibers. Right? That means the force is taken up by fiber and that by your vinyl ester is different. So force is different. So you end up with, again, if you just come into the area taken up or in the concentration with volume fraction, you can identify that they will be taking up almost similar area. So your stresses are different for each, right? Sigma is equal to sigma 1 plus sigma 2. That means series addition, right? So you have to assume equal strain for both carbon and vinyl ester. Okay? Unidirectional is also one of the clues. Unidirectional carbon fiber and vinyl ester. That is also one of the clues. Okay? You're all able to make it? You're all able to understand that? Hello, are you all there?
Yes, ma'am.
Yeah, fine. So equal strain. So sigma is equal to sigma of carbon fiber plus sigma of vinyl ester. That means that is equal to epsilon. So epsilon is the symbol for strain. So epsilon into E of carbon fiber into volume fraction of carbon fiber plus E of vinyl ester plus volume fraction of vinyl ester. Right now, how do you proceed? They have not given the E value, that is a modulus value directly, but they have just given the ratio. So how do you proceed? Very simple. So now the percentage of force taken up by fiber to the total force or total stress. So individual stress by total stress. Here again, since we have assumed epsilon as constant, so again you will have epsilon into ECF into volume fraction of carbon fiber by the total, right? And then here they have not given the value directly, but they have given us ratio. So what you can do is that in case of ECF, that is the modulus of carbon fiber, you can just write it as 35x, and in case of vinyl ester, you can just write it as 1x, right? And then incorporate that. So again x comes out and you can cancel, right? And then you can find out the ratio. So you end up with 97.2% force taken up by the fiber itself, right? Right? Are you all able to understand?
Yes, ma'am.
Okay. Okay. Now, next question. The solubility parameter of polystyrene is 9.1 calories per centimeter cube power half. The solubility parameter of N-hexane is 7.3 and that of benzene is 9.2. Then polystyrene will be It will dissolve in hexane, not dissolve in 80:20 mixture of N-hexane and benzene, not dissolve in benzene, dissolve in benzene. Which one is the right option? This is again a GATE question, GATE 2011 question.
Dissolve in benzene, ma'am.
How do you say?
Because the solubility parameter is somehow close, similar.
Yes, you are right. It dissolves in benzene. Okay? Rest of you are able to understand?
Yes, ma'am.
Okay.
Yes, ma'am.
Chemical aging by photooxidation leads to conversion of C double bond C in natural rubber to which type of bond? CH bond or COH bond or COOH bond or C double bond O bond. This is again taken from lecture.
MC double bond O bond.
Okay, you are right. So photooxidation, this C double bond C is converted to C double bond O. Okay. Let's go to question number 7. This is again a GATE question. For a polymer which follows the Markov equation, various parameters determined were as follows. K is equal to 1.2 into 10 power 4. Eta is equal to 2.4. A is equal to 0.76. Huggins constant is 0.33. And concentration is 0.3 gram per deciliter. So what is the molecular weight of the polymer? Is it 4.5 into 10 power 5? Or is it 6.1 into 10 power 4? Or is it 3.2 into 10 power 6? Or is it 7.9 into 10 power 5? Question number 2 is, what is the specific viscosity of the polymer? Is it 0.73, 1.12, or is it 0.89 or 2.3? How do we proceed with this? At least tell me part A.
Ma'am, intrinsic viscosity is equal to K into M power A.
Yes, that is
The
what is the
formula.
Markov equation. So are all the information except for M. M is a molecular weight, right?
Yes, ma'am.
So are all the information except molecular weight is given?
Yes, ma'am.
Yes. So as you said, intrinsic viscosity is equal to K into M power A, where M is a molecular weight. So you have all the other information except the molecular weight. So you can incorporate it and you will end up with molecular weight as 4.5 into 10 power 5. The second part of the equation is, here you have to use a Huggins equation, where Huggins equation is given by specific viscosity by concentration is equal to intrinsic viscosity plus Huggins constant into intrinsic viscosity square into concentration. Here again everything is given, right? Now calculate and tell me what is the value of specific viscosity. Do you have your calculators nearby?
Yes, ma'am.
So someone can say, calculate and say what is the value.
2.97.
Is it 2.97? Specific viscosity by C. So the C goes to the right hand side. Right? So it will be C into eta plus Huggins constant into eta square into C square. Right?
Yes, sir.
So
0.89, ma'am.
Yes. 0.89 is the specific viscosity. Okay. Okay. Electrical conductivity of doped polyaniline is dash Siemens per meter. Is it 10 power 7 or 10 power 14 to 10 power 16? Or is it 10 power minus 14 to 10 power minus 16? Or is it 10 power minus 2 to 10 power 4?
Option B.
Is it option B? 10 power 14 to 10 power 16?
Ma'am, D.
D, yeah? Okay, 10 power minus 2 to 10 power 14. Do all of you agree with that?
Option D, ma'am.
D or D? Huh?
D. 10 power minus 2 to 10 power 4.
Okay, yes. So it is 10 power minus 2 to 10 power 4. It comes in the semiconductor range. Okay. Higher value of persistent length indicates that the chain is more flexible. Is it true or false?
Oh, false, ma'am.
Why is it false?
Uh, the persistent length says how it is correlated. Like rod-like structure possess high persistent length.
Okay. Okay, do all of you agree with I think Vasu who is the one who answered it, is it? Or Uday?
I mean,
So
so
they, ma'am.
Okay, okay. So do all of you agree? Sorry.
yes, ma'am. It's false.
Okay. Yes. You are right. So as you said, a higher value of persistence indicates the chain is more rod-like or rigid. Okay. You can also see with the values as well. Polyethylene has a lower persistent length. That means it's more flexible. Right? Yeah. Let's go to question number 10. Identify the response variable among the following: stress, refractive index, strain, current, permittivity, light, viscosity. Which are the response variable? Very easy one. If you had gone through that dielectric lecture, you could easily identify this.
Ma'am, you want to match the
No, 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 no.
any two,
I'm
ma'am?
asking you to identify the response variable.
I mean, viscosity is one.
Okay. Is it the only one?
Strain.
And refractive index, ma'am.
Viscosity and refractive index. Okay. Is there anything else?
Ma'am, strain.
Is it strain? Anybody else wants to take?
Permi
Huh?
permeability.
Permittivity. Okay. So some of you have told it right. Some of you have told it wrong. I mean, not perfectly right. Partially, part of the answers you have told. Anybody wants to try? Anybody else? Or shall I say the answer? Okay, I'll say the answer. It is refractive index, permittivity, and viscosity. Someone said strain. It might be either an input or output variable, but it is not the response variable. Response variable here, what does it mean is that it is of the material property. Okay, so refractive index, permittivity, and viscosity are material properties. Okay, are you all able to understand?
Yes, ma'am.
Okay, now question number 11. Scaled response and superposition are features of dash response.
Linear response.
Okay, do all of you agree? Anybody else? Do you all agree scaled response and superpositions are features of linear response? Do you agree? Shweta, Gayatri, Rojbe. I think Rojbe, this is the first time you are joining the live session, is it?
Yes, ma'am.
Okay. Okay. So do you agree with what was told? Are these two the features of linear response? Okay. Anyway, hold on. Significant changes in material structure is a feature of which type of response?
Non-linear response.
Non-linear, ma'am.
Okay. Yes. So both the questions are answered right. So scaled response and superpositions are features of linear response, where significant changes in material structure is a feature of non-linear response. Okay. In fact, the part B we discussed in the recap as well, where we said uh, yield, fracture mechanics, and then electrical breakdown, where there are significant changes in the material structure, are part of non-linear response, right? Yeah. Let's go to question number 12. Match the process with the response of the material. Atomic polarization associated with vibratory modes of atom. Number 2. Molecular relaxation associated with translational, rotational, and vibratory modes of bonds and molecules. Number 3. Electronic polarization associated with electronic relaxation process. So these are the processes. Material responses, conducting response, optical response, mechanical and dielectric response. Now match which one matches with what. This is again taken from your lecture only.
Atomic polarization, optical response.
Okay.
Molecular relaxation, mechanical and dielectric response.
Okay.
And electronic polarization, conducting response.
So do you all agree with that?
Yes, ma'am.
Okay. What about girls? Shweta and Gayatri. Do you also agree? Are you there? Okay. Anyway, you are right. So atomic polarization. Someone has. Yes. Okay. Shweta said yes. Okay. Atomic polarization associated with the vibratory mode of atoms corresponds to optical response. So optical response means what will you identify? What is the response variable? Any idea?
Refractive index.
Refractive index, yes. And then molecular relaxation associated with translation, rotation, and vibratory modes of bonds and molecules, mechanical and dielectric response. Okay. And then electronic polarization associated with electronic relaxation process, it's conducting a response. Okay. Now, in complex conductivity, the real part represents dash of energy, while imaginary part represents dash of energy. What does the real part represent and what does imaginary part represent? This was again discussed in the lecture. Any thoughts? Or shall I say the answer?
No, storage of energy. Uh,
Which one? Real or
uh,
imaginary?
Real one.
Real. Okay, why do you say storage of energy for real part?
I don't know.
Okay, so it is once your material is polarized, what happens? So your polarization energy is stored as a permittivity. Okay, epsilon prime, dielectric permittivity, or okay, and then imaginary part is your dielectric loss. Okay, sorry, complex conductivity. Sorry,
It should come with sigma, no, ma'am? Sigma.
yeah, sigma. Sorry. I'm sorry about that. When it comes to conductivity, your sigma prime is your conductivity, whereas your sigma double prime, it corresponds to epsilon prime, that is your dielectric storage. So, in case of conductivity, real part represents your dissipation. I'm extremely sorry about that. In case of conductivity, real part signifies dissipation of energy, because there's a conduction of electron, movement of electron, right? There's a loss, right? So that represents dissipation, whereas your imaginary part represents storage. Whereas when it comes to your epsilon, okay, your epsilon prime represents storage, whereas your epsilon double prime represents dielectric loss. Okay. In d by relaxation model, if omega tends to 0, then epsilon prime tends to what? And epsilon double prime is proportional to what? Do you remember the plot and all? Plotting and all were done and then it was showed.
Ma'am, epsilon prime tends to ES, epsilon S.
Okay. And then epsilon double prime is proportional to
Infinite.
uh, okay, let me give you one more clue. Whether is it proportional to omega or is it proportional to 1 by omega? Anyone wants to give a try?
Proportional to 1 by omega.
1 by omega? Okay, anyway, let's see the answer. As you said, epsilon prime is equal to epsilon s and epsilon double prime is proportional to omega. How? Let's see. So this is the response of d by relaxation is given by, for epsilon prime, It is epsilon infinity plus epsilon s minus epsilon infinity by 1 plus omega square lambda square. So when omega tends to 0, obviously the denominator here is 1, so you'll get epsilon infinity plus epsilon s minus epsilon infinity. You end up with epsilon s. That is fine. Whereas in case of epsilon double prime, okay, so when omega tends to 0, in the denominator it will be just 1, because your omega square, omega tends to 0, so obviously your denominator is 1. So that means your epsilon double prime is proportional to omega. Whereas when omega tends to infinity, then this 1, the term 1 will, you can get rid of, because this value omega square lambda square will be a very huge value. So what you will end up with is epsilon s minus epsilon infinity into omega lambda by omega square lambda square. So omega gets cancelled, and you will get epsilon double prime is proportional to 1 by omega in case of when omega tends to infinity. Okay? Are you all able to make sense?
Yes, ma'am.
Okay. Macromolecular orientation and creation of polymer microfiber surrounded by voids leading to whitening of sample is called, this is shear banding, hole drawing, necking, or tracing.
Creasing, ma'am.
Do you all agree?
Yes, ma'am.
Yeah. Plasticity model based on the concept of energy barrier for conformational changes. Which model? Which model was based on concept of energy barrier for conformational change? How many models were discussed in the lecture? Do you remember? Just now we had in the recap also.
Ellen mode.
Yes, Eyring model. So this Eyring model is based on, see, it measures activation value, volume, which is based on the energy barrier. Okay, energy barrier for undergoing orientational change. So this concept, so Eyring model is based on this energy barrier concept. Okay. Okay. Now that is the end of the practice assignment sessions. So there were few doubts posted in the forum. One was solution for question number 5 in assignment 5. This was posted by Shivakumar. Is Shiva there around? I don't think he joined today, right?
No, ma'am.
Okay. So was someone able to answer this question and got it right, or none of you attended it? The answers are
That's
released.
half of.
Half of it, yes. Okay. So how did you solve it?
Now the Poisson ratio of the polymer is 0.5. Ma'am.
Is it based on that? Okay. Okay. So only one person solved it and got it right. Okay. Now let's see the answer. So the question is, if rubber cuboid sample is stretched to twice its original length along one direction, the cross-sectional area will be dash its original cross-sectional area. That is the question. So they have given that L is equal to 2 times of L naught. So L by L naught will be 2, right? The new length to original length will be 2, right? That is nothing but your stretch ratio in the x direction, in one of the directions, right?
Yes, ma'am.
Yeah. And then assuming incompressible rubber, that means L naught B naught into W naught is equal to LBW. That is your original length, breadth, and volume. Sorry, length, breadth, and width is equal to the new length, breadth, width. That means that is nothing but your volume is constant, right? So obviously what happens, your stretch ratios will be equal to 1. Multiplying the stretch ratios in x, y and z direction will be equal to 1, right? So lambda SRX, lambda SRY, lambda SRZ is equal to 1 because SRX is L by L naught, SRY is B by B naught, SRZ is W by W naught, right? So that is the thing. Now what information is given? So from the given information, lambda SRX is 2. So lambda SRY, lambda SRZ is, you have to find out. So you already have this. So lambda SRY into lambda SRZ is half. Where lambda SRY and lambda SRZ is nothing but B by B naught into W by W naught. That is equal to half. So you will end up BW, just realignment, you will get BW is equal to half into B naught W naught. That is, new cross section area is half of the original cross section area. Okay, you're able to make sense? Are you all there?
Yes, ma'am.
You're able to understand, right? Okay, now let's go to the next question that was posted in the forum. This was again posted by Shiva only. So he asked for solution for question number 12 in assignment 5. Tensile force of 250 Newton is applied to a cuboid rubber sample of 30 length, having a cross section of 5 by 5 millimeter square. If the length of the sample is elongated to 150% of its original length under the same applied force, what will be the true stress? So how do you calculate this true stress? How do you calculate stress?
Force by area, ma'am.
Okay. So is force given?
Yes, ma'am. 250 Newton.
Okay. What about the area?
Five into five means square.
25 mm square.
Okay. So should we calculate the true stress that way or something else to be done? The major point of the answer lies in what is true stress. Okay. With the information given, what else you can calculate? Okay. Let me solve. So given the tensile force is 250 Newton and then length of the cuboid rubber L naught is 30 mm, area of cross section is 5 by 5 B naught into W naught, that is 25 mm square. Then they've given length of the elongated rubber is L is equal to 150% of L naught, that is nothing but 1.5 times of L naught. From this we can calculate the stretch ratio, right? That is nothing but 1.5, right? Are you all there? Okay. So here again you can calculate what will be lambda SRY, lambda SRZ, right? Because here also you have lambda SRX. And you know lambda SRX, lambda SRY, lambda SRZ is equal to 1. So you will end up with lambda SRY, lambda SRZ is equal to 1 by 1.5, right? Are you all able to make?
Yes, ma'am.
Yeah. Okay. So you have B by B naught into W by W naught is 1 by 1.5. That is nothing but PW, that is the new cross section area, is 1 by 1.5 into B naught W naught, that is nothing but 25. So you end up with new cross section area of 16.67 millimeter square. Now tell me, to calculate true stress, should I take 16.67 or should I take 25 mm square? Did anybody solve this problem in assignment 5 and got it right? Any response? You can say yes or if yes means yes, no means no. There is nothing right.
No, ma'am.
Okay. Now let's proceed. True stress is actually applied load by actual cross section area. Now what is the actual cross section area here? Cross section area after the force has been applied and how the material has become deformed. That new cross sectional area. Okay. So here you have to take true stress is 250 by 16.67. So you will end up with the value of 15 Newton per millimeter square. That is a true stress. So if you have some concept of true stress, there is also some concept called engineering stress. Okay. In this engineering stress, how do you calculate the stress is that it is applied load by original cross section area. So original cross section area is 25, right? And your load is 250. So what you will end up in a engineering stress is 250 by 25, that is 10 Newton per millimeter square. Okay. That is why they have specifically asked what is a true stress. Okay. In case they ask what is engineering stress, then you have to use the original cross section area. Are you all able to make sense? This one you would have even gone through in your material science course. Okay. So that's it for the day. Thank you all. Have a nice evening. Okay.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank
Thank
you.
you, ma'am.
Thank you. Any other doubts you have? Okay, all of you left. Fine. Anyway, thank you.